Good afternoon. My name is Naomi Crump, and I'm an analyst here at the Danish Emergency Management Agency, also known as DEMA. Today I'm going to present to you our project on fire probability mapping for the prioritization of fire prevention efforts. I would like to start by thanking our collaborators over at the University of Copenhagen for all of their hard work and time. And of course, I'd like to preface this presentation by saying that at the time of this recording, we are midway through our analysis. So what you'll see today is not our final results, but rather our expectation of what we'll be able to show you as an output at the end of our analysis. And with that, I'd like to give you a little bit of a structure of what you'll see today. First, we'll talk about why we're conducting this analysis and how we got to this point. Next, I'll talk to you about our data source, as well as the methodology that we've chosen for our analysis. And then to conclude, I will talk more about our expectation for both the statistical and the predictive side of our analyses. And as I mentioned before, there will be some time for discussion where I hope that we can also give you a little bit of information on the results we expect to have between here and now, here and then. So with that, why are we conducting this analysis? In the last decade, there have been over 58,000 building fires in Denmark, with over 600 of those being fatal fires. That is a fire where the victim actually perished within 30 days of sustaining a fire-related injury. As you can see from my figure here, this is the percentage breakdown of building fires by where they actually happened in the last decade. And it's true in Denmark, but also many of the other Nordic countries, that the top two locations of fire are private residences. That is houses, blocks of flats. So this gives us already some information that we should be looking into the demographic and people-related side of fire. We also know from literature and theory that demographics are often a high risk factor when you're talking about the prediction of fire. We know, for example, smoking is highly correlated with the incidence and occurrence of fire. So we began with a pilot project that started as a master's thesis at the University of Copenhagen. While we conducted this, we were actually selected for an EU grant related to disaster prevention and preparedness. So you can see already that there's this establishment of a need and a desire for this sort of analysis. And so what we expect is to be able to look into these population-related factors in Denmark and actually create a tool that can predict fire and also give us a more complex understanding of what's going on in the study area. With that, I would like to tell you more about our data set. And this is one of our biggest assets, the data that we've acquired for this project, actually. I'll begin with the occurrence of fire, which is the phenomenon that we're trying to explain and predict. Now, this is sourced from here at DEMA. We have a database called the Odin database, which houses our municipal fire brigade callouts. And so between the years of 2016 and 2019, once we've cleaned and filtered the data, we have around 20,000 fire incidents to use. And this is without regard to severity, but simply whether or not the fire brigade was present at the scene of the fire. And we do that because of sample size. We want the highest sample size we can have at this point in time. Next, we have our geomatic demographic variables. Now, Geomatic is a Nordic data analytics company housed in Denmark. And what we have from them is around 140 demographic variables related to education, employment, income. We also have a set of variables called the consum variables, which Geomatic has actually segmented this from the population themselves. And these are more specific niches in Danish society. They give us more information such as the purchasing habits, recreational activities, family structure that these groups might be engaged in. And you can see that this is probably a really good way for us to get information that are not readily available in other variables. Finally, we have our building and property variables. And this we source from something called the BBR and ESR. That is the National Danish Building and Dwelling Registry, as well as the Property Registration Database. And what this holds is a large amount of variables related to, say, property value, construction year, building usage, ownership type, and even such specific variables like heating installation, energy source, even the exterior wall material that a building might have. So we have a very good data set here, and we also have a very high spatial resolution. As you can see from our image, we're working with a 100 by 100 meter grid cell set over the populated areas of Denmark. So this is a very big asset to us, and this is how we've conducted our analysis. Our methodology actually takes place in 2 phases. And this is for 2 very separate reasons due to the assets and limitations of both sides, as I'll get into. On one hand, on the left here, you see our statistical regression analysis, which is used to create our explanatory model. On the other side, we have our machine learning analysis, which of course is used for our predictive model. So I'd like to begin with the statistical regression side. We're conducting this in order to give a very good understanding to us about the strengths and natures of the relationship between fire and the potential risk factors in our study area. Of course, with a regression analysis, there are certain data assumptions which must be met, which is our limitation. Therefore, this will be used to give very specific risk profiles to our fire brigades and inform them on how best to target these risk groups in the population. On the other hand, we have our predictive analysis. Now, machine learning algorithms are typically, they're able to produce a higher predictive power than regression. And this partly is because they're not sensitive to the requirements that regression is sensitive to. For example, we're able to incorporate a much wider array of variables than we would be in a regression analysis. The trade-off, of course, is that this is a black box, and there's little to no information on how these variables interact with fire in the study area. Therefore, this will be used primarily for our visualization tool and to get the highest maximum predictive power for our mapping endgame. Now, I'd like to give you a bit of an insight into what we expect from our statistical analysis to begin. And to do this, I'd like to reference the pilot study that I mentioned earlier. Now, this was a study that took place in Aarhus, Denmark, as you can see on the map there. It only incorporated demographic variables and on a smaller set than we see in our own larger data set now. But what we learned from this study is that 3 of these demographic variables were significant in their relationship to fire, and that was low education, living alone, and low income. We see that when these rise in the study area, so does the probability of fire. We could also see that low education exerted the highest influence on fire prevalence, followed by living alone, and then finally, low income exerted the least influence. So from this, we got a very specific picture into Aarhus related to the demographic variables there. Now, in our current study, we're working with, of course, the whole of Denmark. We've, as I've mentioned before, incorporated building and property data as well as a much larger array of variables for the demographic side. While we're still in progress with the regression results, I can give you some features that are important right now in the prediction of fire prevalence in our study area. And what we're seeing now is primarily those are building and property variables, such as property value, construction year, building usage. Is it a detached family home, or is it a condensed set of apartment blocks in the middle of the city? These are showing to be very important in our model. We've also seen that some of the consume variables I mentioned before are significant, but we need to look more into why that's happening. As I said before, they hold a lot of info within them. So yeah, what we expect from this is something similar to the pilot study, that we'll be able to know the specific nature of those strengths and relationships to fire. Now I'd like to talk about our expectation for the predictive analysis. And for this, it's quite exciting that we're creating an interactive tool for the municipal fire brigades. This will allow them to visualize the distribution of fire probability within their municipality. We anticipate some workshopping events in order to enhance the functionality and design of our web-based map interface. And the expectation would be that we can give access to a couple users within the municipality fire brigades, each one, who would be able to have a high functionality with little to no software training. Now, of course, we haven't settled on our final user design for the map itself, but I can show you what we may be able to expect from the visualization of these results. And you can see here this map on the right. This is an excerpt from the pilot study again. And you can see here on the map that probability has been visualized within the 100 by 100 meter squares in Aarhus. And this is based on how the demographic variables were distributed within those grid cells. So from the equation output, you can see that a darker red area corresponds to high fire probability. A light yellow area corresponds to low fire probability. Now, we expect to be able to conserve this level of simplicity while also enhancing the user experience and making a very interpretable output. And with that, I would like to open things up for discussion and questions. I'm really interested to hear your feedback at this point. And I would also like to thank our collaborators at the University of Copenhagen once again, and just open things up for discussion. Thank you for your time.